continue with our lecture videos on calculus. In the previous one we did the limit definitions of derivative, or the first principle. If it becomes difficult to do, then the rules of the game should help you get the same work done but with ease. The rules are given in slide 9. We have the power rule, the sum rule, the product rule, the quotient, reciprocal, chain, and implicit. In this lecture video, I'm going to take the first 3 for you to make it easier. Let me just change the pen to, I think blue should just do. Before we move to this 3, look at what we have in slide 10. They are derivatives of special functions. So we have the exponential function, the trig, that's cosine, we have the logarithm, we have another exponential form, that's ax. You can derive the derivatives on the right side of the column of the table with the first principle of differentiation. So let's have a proof of the very first one. It says that if I have derivative of an exponential ax, is given as aeax. How do you want to prove that? I want to prove with assuming a is equal to 1 for you. So that means that the function is equal to ex. And then my f of x plus h should be equal to ex plus h. From the limits, first principle of differentiation, I have the limit as h approaches 0 of ex plus h minus ex all over h. By indices, you know you can do something to this guy. You know you can multiply. By indices, if they are adding, it is simply multiplying, and if they are multiplying, it is simply addition. What can I do from here? I can factorize my e to the power x out and have e to the power h minus 1 all over h. So it's as if I have limit as h approaches infinity, 0 of ex, multiplying the limit as h approaches 0 of the other part of the equation. As limit approaches 0 here, I'm going to get e to the power x because there's no h term to do the substitution. The limit as h approaches here, we're going to get 1. And so e times 1 is ex. And indeed, the derivative of this is just equal to the same guy here. Now you want to go to the same approach and assume that a is not equal to 1. So it means I have ex. It should fall in places for you. And so they are not magic. You can use the first principle to prove all these special derivatives. On that note, let's quickly take the rules. The first 3 rules. The power rule from slide 11. The power rule says that if I have to differentiate a function which takes an index n, where n is a raw number, so it means from the negative infinity number to a positive infinity number on the entire raw line. Okay, it says have the n here, have your x, and then subtract 1 minus the numerator. As simple as that. So your n is being multiplied here, and that same n is subtracted from 1. And that is a power rule. So let's take a quick example. As I have a table here, table 11. So x, what is the derivative of 12? Here it's assumed that I have x to the power 0. So the first derivative gives me 0 times the 12 remains x to the power 0 minus 1. Because the number is multiplied by 0, automatically I have 0. And this brings us to the first rule. The derivative of a constant is always 0. The derivative of a constant is always 0 by the power rule. Okay. Example 2, I have a function x. I want to find the first derivative. This is the same as x to the power 1, but we don't write x to the power 1, you know that. And so the first derivative gives me 1 multiplying here, x to the power 1 minus 1. What do you get? You have 1 times x to the power 0. And number to the power 0 is 1, and so that is 1. The second derivative, it means I'm differentiating 1. We've confirmed that derivative of a constant is always 0. If I find a third derivative, I'll still get 0, on and on. The third example is the last example under the power rule. I have x to the power 5. Now the first derivative gives me 5 times x to the power 5 minus 1. That is 5x to the power 4. The second derivative, I have to now differentiate this guy. the second time gives me 5 times 4 x to the power 4 minus 1. And what do I get for that? 20 x to the power 3. If I want to find the third derivative for this, it's as if I'm differentiating the resulting function, 20x cubed, and I'm going to get 20 out, 3 x to the power 3 minus 1 by the power rule, and 20 times 3 gives me 60 x squared. You can go on and on to get the derivative to be 0, and that is how simple the power rule is. Now let's take a case where I have x to the power 2x 0.3, 2 to the power x 0.3. It means I'm going to get 2 out here, 0.3 x to the power 0.3 minus 1, and what do we get? 2 times 0.3 gives us 0.32. So when you get 0.6 x to the power 0.3, negative 0.7, and so x can be any number at all. Yours is to be able to use the power rule. Let's try 3 x to the power 1 over 4. 3x to the power 1 over 4. It means by the power rule I'm going to get 3 out here, 1 over 4 times x to the power 1 over 4 minus 1. And what do I get for the multiplication? I'm going to get 3 on 4 here, x to the power, you should know what to do here, and that gives you your power rule. Okay, now let's move on to the sum and differences. With the sum and differences, we can add 2 terms or subtract 2 terms, just as we did in polynomials. So if you're adding 2 functions, it says first do the derivative of the first guy plus find the derivative of the second guy. You can have more than 2 terms, assuming I have f plus j plus h or minus z. What I have to do is to first find derivative of f, add it to derivative of j, add it to derivative of h, minus derivative of z. That is how the sum and difference rule is applied. So exactly, let's take 3 examples and then we move to the last thing. Example 1, I have x to the power 4, 6x to the power 11. You can do this by a power rule. So I'm going to get 4x to the power 3 plus 66x to the power 10 as my answer. The second derivative of this guy, I'm supposed to get 12x squared plus 610 or 660 of x to the power 9. Okay, the third derivative. I'm going to get 24x plus 5940 x to the power 8, and so on and so forth, just by the power rule. Example 2, if I want to find the first derivative of this guy, the first derivative should give me 3v squared minus 4v cubed. The second derivative by the power rule should give me 6v minus 12v squared. The third derivative by the power rule should just give me 6 minus 24v. So here square minus 24v. Let's take the fourth derivative. I should get 0 because derivative of a constant is 0. So I have negative 24. And I can go into find a fifth derivative which will give me 0. And so that's how the sum and difference rule is applied using the power rule. The last example. So the last example, I'll leave it for you to try your hands on, and then you should just comment in the section what your first derivative are, your second derivative are, and then your third derivative are. Okay, and you'll be good. So let's move to the last episode, or the rule, the product rule. The product rule says if I have a function of f of x which is given in this form, I have u of x and v of x multiplying. They are not just multiplying for fun, but they have a common variable of interest. They all have x in it and they are multiplying. I have to use a product rule. The product rule says that first maintain your u, differentiate the v of x. When you are done, maintain the same v, but now differentiate your u of x. I hope that is clear. So I still have the u maintaining here. This guy becomes v prime plus maintains here, v maintains, and then this becomes u prime. So that is it for the product rule. Now you want to take note, just because we said the sum of two functions is the same as find derivative of the first plus derivative of the second, doesn't mean that if I'm multiplying these two functions, it means find derivative of the first one and multiply by the second one. This does not hold. So that's what I have for you here. You have to use the product rule. Okay. So again, we'll take the first two examples and then we'll move to an interesting part of our journey. Example 1. I have the function given as x e to the power x, and what do? Why am I going to use the product rule? Because my u is x, my v is ex. They are all in terms of x, so I have to use the product rule. So I maintain x, and what do I differentiate? Ex, plus I maintain this ex now and differentiate the x. So let's quickly do that. X maintains derivative of exponential function still gives exponential. We've proved this. You maintain this ex, derivative of x by the power rule gives you 1. And so let's see what we are going to get at the end of the day. I have x ex plus ex. You can go ahead and find a second derivative of what we have here, the resulting function. And so this is where the sum rule comes in. But for the first part, it's still going to be a product rule. So x maintains, I differentiate ex, plus ex maintains, I differentiate the term x, plus the last guy. That is not of any product rule, it's just of itself. And you can tell that I'm going to get x ex plus ex plus derivative of this is ex. So that's going to be x ex plus 2 of ex, and you can go on and on with this derivative. So I ended here. The second example, example 2, I have a function given as sine x and then cos x. Why is it a product rule? I have my u of x as sine and I have my v of x as cos, and because they are multiplying with the same variable of interest, I have to use a product rule. So the product rule formula: maintain the first guy, differentiate the second guy. Maintain the second guy and differentiate the first guy. That is as simple as that. And so we have sine x, derivative of cos is negative sine. I maintain my x cos here, derivative of sine x is cos x. And so at the end of the day I have negative sine square x plus cos square x. Believe you me, this is never equal to 1. From the trig identity, it is cos square x plus sine square x giving you 1. So that is your answer. You can go ahead and find the second derivative, the third derivative, the fourth, and so on and so forth, just by the product rule, as simple as that. Now the last example, the teaser. It is given that you want to take your time for this teaser. You have f of x given as that. You have g of x given as x. It says evaluate h given as f of x times g of x. You will simply say this is the same as s cubed times x. Okay, I have x to the power 6 from the question. And this is the same as my u of x. This is the same as my v of x. And so I'm going to use the product rule. Let's look at something here. This h of x is the same as having an x to the power 11. X to the power 9. Why? Because by indices you must add this exponent, and so my first derivative simply does not have to use the product rule again. I have to use the power rule. So the second derivative I have to use the power rule, and I get something else, and that is it. So you have to be smart in when to use the product rule. 72 x to the power 7, and when not to use the product rule, and so on and so forth. And so that is it. Now to the utmost thing of the day, our problem of the day. Our first problem of the day under derivative. This problem has to do with an economist who has established how price of tomatoes behave on the market or respect to market behavior. It says it is modeled by this, so small p of x is given as that from the economist. He went to the market to interview a lady at random, and she says, do you know what I do? I make profit of 10 to 50 pesos on each bucket of tomatoes I sell. So that is from a trader's point of view. And so you can model it as what we have, the capital P. But the question says, what is the marginal profit? What is the marginal revenue of the bucket sold? And then interpret your outcome. Marginal has to do with the gains for an extra production or extra sales, like extra of doing something. So if I want to find a marginal profit, I want to find a small change in profit. The small change in profit on extra bucket, on each extra bucket I sell by the woman. Small change is where derivative comes in. So you must figure out, is it the small p or the big P, and find the derivative of that, and that gives you your marginal derivative. So it's a derivative of something, and that gives you another thing, and interpret the results. The second one says the marginal revenue. Marginal revenue means the additional revenue we make from sales, from extra sales made. But we are not given a revenue function. You have to find it. And revenue is given by quantity times price. The quantity was X, and then the price was a capital or small p. You must be able to figure it out. And so this is our revenue. Now the measure becomes the small change, so ddx of r of x. If you're able to find this function, then you can find whatever I had with at. So let me clean this. Becomes ddx of r at 5. Oh, there's no right representation. Whatever answer you had, you have to substitute 5 here and then find the marginal revenue at 5. So this is how we tackle the problem of the day. You must know when to use the product rule, when to use the power rule. You must comment here, are we using the power rule, are we using the sum rule, or are we using the product rule? And here too, are we using the power rule, are we using the product rule, are we using the sum rule? What are we doing? Interpret your results. So let's have that in the comment section, and then let's see how well we do with our derivatives. On this note, I end here. In the next session, we are going to take 2 last rules. Again, if you've not subscribed, you know what to do. Subscribe and let's have fun with our education. Thank you.